Okay, welcome back. Now we know how to construct a hypothesis testing. So let's take a look at how we can do actually one sample t-test. So when I say one sample, I should make it clear that we are talking about making an inference based on a data from a single population. For example, if you are interested in testing a population mean, based on a specific sample that you get from that population, that would actually fit into one sample tests, okay? The example that I gave in the previous video about making a claim on the average height of Florida Southern College students, so that would be, our population would be in that example is the entire set of Florida Southern College students, and the sample that I might have is just people in this class, right? And I will be just measuring the average height of the people attending in this class, and I can go back and try to make an inference about inference on the entire population height. So if you have that kind of scenario, then you have only one sample from one population, and you're trying to make a claim on the population parameter, then you would be doing one sample test, okay? So one-time sample test can be done in t-test or z-test. And z-test, and both of them assume that the data is coming from a normal probability distribution. And I'm going to show you how to test normality in a moment. What is the difference between z-test and t-test? So in z-test, we assume that we do know the population standard deviation if we are testing population mean. Most of the time, we cannot be sure about the population standard deviation unless we have the entire data for that population, okay? That's why I'm not showing you the z-test, I'm jumping into t-test. I want you to focus on the three different hypothesis testing on the slide. So remember, we said that alternative hypothesis, sometimes it is, the notation is HA or H1 for alternative hypothesis. H0 is basically H null. Okay, those are the two different notations used for H0 and H1, or null hypothesis and alternative hypothesis. But I want you to take a look at the signs that we have on alternative tests on these two different structures. As you can see, in the alternative hypothesis, let's assume that we are working on population average or population mean, right? And we indicate it by the Greek letter mir, right? We always use Greek letters for the population parameters. In this case, we are talking about population mean, all right? And then mu0 in this case just can be any constant. Mu0 can be 5, 10, 100, whatever you are measuring, okay? Let's focus on the alternative hypothesis sign, all right? So the alternative hypothesis signs can be less than, right? If your alternative hypothesis is less than, for example, you're claiming that your population mean is less than a constant, then your sign in the null hypothesis should be just the other way around. And it must include equality in the null hypothesis, all right? We don't put equality in the alternative hypothesis, we put it in the null hypothesis. That is one important feature of hypothesis testing. Again, the first stage is to correctly put together the null hypothesis and alternative hypothesis, all right? So if your if your alternative hypothesis has less than sign, then we are actually doing a less than hypothesis testing, one-sided less than hypothesis testing, meaning that if you look at the normal bell curve, so this area on the lower left tail is actually the critical region, right? If it is not equals to, right, if you have this not equals to sign in the alternative hypothesis, remember just the opposite of this one is just equals to, right? In the null hypothesis, then it is actually two-tailed one sample test, right? And if you look at the alternative hypothesis sign here, greater than, then it is actually your critical region is here. You will have to calculate the test statistic and see whether your test statistic falls into this critical region. If so, you will have to reject the null hypothesis. But we are not going to go into that path. We are going to come to conclusion much faster based on the p-value, which will be explained later on. In a nutshell, this is one sample t-test, hypothesis testing different structures. So we might have 3 different structures depending on the sign that we have on the alternative hypothesis. As I said, both null hypothesis and alternative hypothesis should cover all range of possibilities on the population parameters, in this case, population mean that we are testing. If you put population mean less than a specific number, then in the null hypothesis, we have to put greater than or equals to, right? And if you put not equals to, right, and then we have to put just opposite of it to cover all the ranges of possibilities, and that is equals to, right? And in the alternative test, in the alternative test, we do have, if we have greater than sign, and in the null hypothesis, we have to put less than or equal to, right? So that's why we usually start with the alternative hypothesis, our claim, the alternative or the proposed changes. We should be very careful when we are putting that claim together for the alternative hypothesis, because whatever we propose in the alternative hypothesis test, we are going to propose just the other way around in the null hypothesis. Um, Before I go further down, I would like to talk more about potential errors that we might make when we are doing statistical testing. So remember, we have only 2 hypotheses, right? One way or the other, right? So in this case, we are not sure. Let's assume that we are not sure which one that we should go with. And let's assume that we failed to reject the null hypothesis, but actually the null hypothesis is true. In that case, we are making the right call, right? We are not making any error here. What happens? Let me get this out of the way. So what happens if we are actually failing to reject the null hypothesis, making sure that we are not rejecting it, but actually the alternative hypothesis is true. In this case, we are making an error, and that error is called type 2 error. This error is very hard to handle. That's why we focus on the other error that we might be making in our situation. And that error will be if the actual situation is telling us that the H0 is true, the null hypothesis is true, and we are actually rejecting it, we are actually obviously making an error. Let's assume that I am testing the average height of those college students, and then I claim that it is actually equals to it is actually equals to 175 centimeters, and it turned out that it's not true, and I still well, if it is true, and then I just rejected that claim, then I'm making a type 1 error. Okay. And if I'm actually not rejecting it, and then the alternative is true, in this case, I'm making the right call. All right. Long story short, the type 1 error that I make is actually called alpha. All right. And alpha is also the level of significance of the test that we might be doing later on, right? So that's referred to as the probability of rejecting the H0 when H0 is true. If that probability equals to your alpha, and then you can control alpha much more easily compared to controlling the type 2 error. And that's what we are going to be doing. So we call it level of significance. And the alternative, the type 2 error, is labeled as beta. And 1 minus beta is actually the power of the test, but we don't have to go into specifics on that side. So long story short, we do have error margins in statistical tests. One thing to be aware of is the fact that we can control actually the probability of making a type 1 error. And the type 1 error is rejecting the null hypothesis when actually the null hypothesis is true. All right, and that is actually a percentage, and we do control that percentage before even we make tests, right? It is in our hands. So actually, let's see in practice what we have learned so far. And these couple slides, I'm going to show you how you can construct the null and alternative hypothesis. All right, so let's read this example together. So it says that research finds that today's undergraduate study an average of 14 hours per week. And we randomly selected, and this is the status quo, right? So research, tells us that. And randomly selecting, we would like to challenge this to see whether it is correct or not. Randomly selecting 35 Florida college students have been selected and asked their average study time per week in hours. And the dean would like to test if the mean study of time students differs from 14 hours per week. Again, alpha is the probability of making a type 1 error, and equals to 5%, and it is also called significance level. And 1 minus alpha is going to give us the confidence level of this test. So you might be confused a little bit at this point what alpha is and what 95% confidence is. Just assume that we can control the type 1 error, and type 1 error, remember, is rejecting the null hypothesis when the null hypothesis is true. As I said in the previous video, so we start with constructing the alternative hypothesis. In this case, we have to really tell us what the current status quo is and how we can challenge it. Well, if you pay attention to this text, you realize that the study actually suggests that an undergraduate student study an average of 14 hours per week, and that's the status quo. And the dean would like to really test whether this is true or not. And the way that he or she would like to test it is selecting 35 students and then asking them, how long they really study in a week, and hopefully taking the average of it, like taking the mean or taking the average of that sample, and hopefully be able to make a judgment inference on the population, the entire student body. Okay, so in this case, well, the dean is interested to see if the time of study time of students differs from 14 hours per week. It doesn't say less than, greater than, it says differs from 14 hours per week, right? Therefore, the dean's claim would be in the alternative hypothesis, which is mu not equals to 14, okay? And based on the alternative hypothesis, we do have 3 different options. It can be not equals to, less than, or greater than. Then we include equals to sign on the null hypothesis. In this case, it would be mu equals to 14. And mu stands for the population parameter, the population mean. In this case, the average study time of the entire student body in our college. Okay, and therefore this is a two-sided test because having non equals to sign in the alternative hypothesis gives us these 2 critical regions, and it is called actually two-sided test. All right, that is just one example. And let's switch to other one. And here we do have a retailer operation. So the retailer states that customers are complaining about underfilled bottles, and some customers state that the bottles that they bought contain less than a gallon of milk, and we are expected to use probability of type 1 error alpha as 5%. And here it says that let mu be the average amount of milk in a bottle. And how do we go with this? Again, what is our status quo, and what is the alternative that we would like to be testing? So in this case, customers state that the bottles that they bought contain less than a gallon of milk, right? They are challenging our status quo. So therefore, we have to represent this in the alternative hypothesis, right? And H1, the alternative hypothesis, is constructed like this one. So if our mu represents the average amount of milk in a bottle, and the customers are suggesting that it is less than a gallon, well, we put this situation in the alternative, and we put the other way around the symbol, greater than or equal to symbol, just to cover all ranges of possibilities in our hypothesis testing in the null hypothesis statement, right? So our alternative hypothesis is actually the claim, the alternative version, the customer suggestions, or the claims or complaints, whatever you want to call them. And H0 suggests that this is our status quo. right? And this would be based on the sign on the alternative hypothesis testing. Look at this. It is actually less than hypothesis test, right? It is one-sided only. All right. Okay, and we have another example. This time we also have data for it, and we are going to be using Minitab to deal with this problem. But let me pause here and give you the time to ponder what we just learned.